Everyone, my name is Hao Tianshi. I'm a PhD student from Temple University. I'm so glad to present my work titled PFirewall, Semantics-Aware Customizable Data Flow Control for Smart Home Privacy Protection. This is a joint work with Dr. Qiang Zeng, Dr. Xiaojiang Du, and Dr. Lanan Luo. Smart home is a typical area in Internet of Things. In smart homes, dozens or hundreds of IoT devices are connected to a platform to provide specific services. The most common ones are remote monitoring and control and home automation. In remote monitoring and control, users are able to view and change the states of IoT devices through a given web or mobile interface. Home automation adds intelligence to smart homes by allowing the automatic control of smart home devices. For instance, the smart home can lock the door automatically when it detects all the users leave, or it can adjust the air conditioner based on the motion and the room temperature. Automation rules are usually defined on mobile companion apps provided by IoT platforms and are executed reactively on the platform, following a trigger condition action paradigm. To run a trigger condition action rule, the IoT platform listens to all the events sent by the IoT devices. When an event is received, it will be broadcasted to all the automation rules running on the platform. The platform also uses the event to update its database, which stores the current state of the corresponding device. When the incoming event satisfies the trigger of a specific rule, the rule will be activated. It then proceeds to check its condition by querying the database on the platform to obtain the state of the related devices. If the condition is evaluated to be true, the rule will finally perform its action by sending commands to the IoT devices. IoT events are quite sensitive, and if leaked, could be exploited to infer the homeowner's private information. For example, events from a presence sensor tells if the user arrives or leaves the home. Data from motion sensor indicates that if the user is active at a specific location in the home, and the states of appliances can be used to learn the occupancy habits or activity patterns. In current smart home systems, the good thing is that the transmission of events are encrypted. However, the bad thing is that there is no access control between the IoT devices and the platform. Thus, when devices are connected to the platform gains the access to all the data. Also, the users don't have any capability to control the access of their data. What's worse, we have observed a lot of vulnerabilities, attacks, and failures that make us unable to assume that the platform is completely trusted and able to protect users' data. This motivates us to consider a semi-trusted model, that is, the platform faithfully provides services but may be curious to mine users' privacy based on the exposed data. Accordingly, our research goal is to achieve data minimization and user-centric control. First, only data that are required by the home automation rules are exposed to the IoT platform. Second, users are able to control their own data. We choose to design a third-party solution instead of a patch for the IoT devices, platforms, or protocols, because we consider that the stakeholders may lack sufficient incentives to deploy the privacy protection solutions due to a lot of practical reasons. And also, as the privacy protection is an urgent issue, we'd like to avoid the lagging deployment due to the long time to market or the out of steps among different stakeholders. Thus, a challenge we have to solve is that how to reduce data leakage in a closed system where none of the devices, hub, communication protocols, or the platform are modifiable. To address the problem, we develop a man-in-the-middle style proxy to mediate the communication between IoT devices and the platform. Here's an overview of our solution, PFirewall. PFirewall consists of 3 modules: a device connector, a policy-based data filter, and a platform connector. We design a customized policy format since we cannot find a direct fit in the current access control policy languages. Each policy, as shown in the top right picture, uses a number of fields to express multifaceted information about how to filter IoT data. Basically, the policy is a whitelist style one which defines which data under which situation can be reported to the platform in which way. Except the data allowed by the policies, all the other data received by PFirewall will be blocked by default. Besides, we give a policy engine which parses and executes all the policies. Instead of explaining the complex policy format and the parsing algorithm, I will use examples in the following slides to explain the idea of data filtering and policy design. I'll first explain why IoT data are redundant for executing automation rules. Consider a rule example. When a presence sensor PS1 becomes present if the reading of a temperature sensor TS1 is higher than 86, then turn on the fan F1. Suppose only this single rule is installed for a room. In existing system, not only the 3 related devices, but also all the other devices will report all the data to the IoT platform. So the platform collects all the reported data. But in fact, let's rethink the automation rule. Actually, all the unrelated devices are not necessary. The data from all the unrelated data are unnecessary at all. And even for the 3 devices, in most cases, for example, when the presence sensor detects nothing or the presence sensor detects not present, or the temperature sensor detects the temperature which is lower than 86, or the fan is already working, there's no need to report any data to the platform because the automation rule has no need to run to turn on the fan. And even in some situations, the automation rule is needed to be run. We don't have to report all the related data to the automation rule. For example, we don't have to report the temperature value if the last reported value is already higher than 86, because the platform can use the old value to produce the result correctly. So in summary, only sporadic data points in the data streams are required for executing the automation rules correctly. To filter the redundant data, each AP, the automation-independent policies, is defined to only feed the necessary data for a rule. As shown in the right picture, we derive a NAP from the running rule example by a simple matching of the rule semantic information to the fields of the policy. This AP expresses the conditions that must be satisfied for reporting some data and the methods for reporting each piece of the related data, following the ideas we have discussed in the last slide. Besides APs, which are generated automatically, will also allow users to specify policies on the given templates on the mobile app to fulfill their own privacy preferences. The app lists all the devices that are connected to the PFirewall. The user can view all the data types supported by each device. Then he can define the policy for each data type, such as always or never report this type of data, or only report the data during a specific period of time, or define advanced control like start or stop reporting this data upon a predefined event. To enforce the data filtering in a closed system, PFirewall is implemented as a man-in-the-middle style mediator. The device connector and the platform connector work collaboratively to achieve this. In the original system, devices have three basic interactions with the platform: join or leave, exchanging events, and exchanging commands. Thus, PFirewall needs to handle these interactions. Specifically, when a device pairs with the device connector, the platform connector will register a virtual device instance to the platform to represent the real device. When this device unpairs, the corresponding virtual device will be unregistered from the platform. Thus, when the device sends an event to the device connector, the event will be fed to the policy-based data filter for processing. If the policies decide to report some data to the platform connector will then use the corresponding virtual device instances to report these data to the platform on behalf of the real devices. Due to the time limit, I will skip the implementation details in the presentation. Details can be found in the paper. To evaluate the performance of PFirewall, we set up 4 real-world testbeds, including 1 office and 3 apartments. In each testbed, 1 platform and tens of devices are deployed. Besides, several automation rules are installed in each testbed to control the devices based on the demand of the testbed members. We tested 3 major performance metrics of PFirewall: correctness, data reduction ratio, and latency by running each testbed for 1 week. The correctness shows if the data filtering can guarantee the correctness of automation rule execution on the platform. Results show that PFirewall does not influence the execution of the automation rules. We also evaluated the ratio of data that are blocked by PFirewall, namely the RR in the table. On average, over 97% of the raw events are filtered by PFirewall. We also defined 2 metrics, CTR and CATR, to evaluate the ratio of time periods during which the device states can or cannot be tracked correctly. The results vary with the device type and the automation rule setup in each testbed, but overall, PFirewall disables the tracking of most device states by more than 50%. PFirewall introduces a latency of about half a second to the automation. Considering most automation rules are not time critical, this is an acceptable trade-off for more privacy gain. Now that data filtering significantly reduces the amount of data that are exposed, to further evaluate how much privacy is actually gained by the data filtering, we consider the inference attacks that use heuristic methods in the left table to infer users' activities based on the exposed IoT data. The heuristics are derived from several existing papers about activity recognition. We test the performance of activity inference with and without data filtering. The 4 confusion matrices in the right picture show that the data reduction significantly impairs the capability of inference attacks in 2 testbeds, T3 and T4. This brings me to the end of my presentation. I've talked about a policy-driven approach to filter IoT data for privacy protection in smart homes. To enforce the approach in closed IoT systems, a proxy is developed at a vantage point. We believe this design can be widely utilized to enforce third-party security and privacy solutions. This work is evaluated on a real-world basis. The results show that IoT data can be reduced and the privacy can be enhanced significantly by DataFlow control without impairing the original service. Thank you for listening. I'm glad to answer any questions.